Hello everybody! This video is part of the series of videos Exploratory Computing with Python. In this video I discuss 4 exercises and solutions. You should be able to do these exercises after working through Notebook 1 through 4. My name is Mark Bakker and I work at the Delft University of Technology. We start by importing NumPy as NP, importing matplotlib.pyplot as PLT, and telling IPython to put all figures in line. Exercise 1. Smooth interpolation may be carried out with what is called a radial basis function, like the following. Y is equal to the sum from small n is equal to 0 to capital N of an times the square root of x minus xn squared plus d, where capital N, an, xn, and small d are parameters. The question is, plot y versus x for x varying from 0 to 8 using the following parameters. Alright, let's start doing that. First we have to define those parameters. So we type in n is equal to 8. We want to copy this an and xn from this markdown cell. If you double click on that, we can simply edit this, copy an, and we're going to call that variable a, so that's going to be a list in our case, and we copy xn, and we call that x. So we get rid of the underscore n, and finally we say d is equal to 2. Let's make it 2.0. We go back to this markdown cell, we hit shift enter, so it turns into the markdown language you want to see. And here we have now a and x. Just to make sure that a and x are the right length, let's print the length of a and the length of x to the screen. Let me see, we get 9 for both, and that's correct because they go from 0 up to capital N is equal to 8. Now let's try to calculate for x from 0 to 8. X is np.linspace 0 to 8 with 100 terms. We want to calculate y in this summation. That means we first have to make an array y filled with zeros and then add all these terms in the summation. So y is equal to np.zeros, the same length as x. Now you see we have a little problem because we call this x, and also these xn's we've called x. So let's call this the x where we want to plot things, xp. So this x in the formula here will be called xp. So then y is 0's length of xp. And we do a loop for I in range n. Well, not n, because we also want to include n, so it's n plus 1. Right, here in the summation we also want to do capital N, so we have to do for I in range n plus 1. Y is equal to the y we already had, so we say plus equal, and then we want to add this formula. A number I, well, let's call that in for small n in range, so that it looks like that formula. An times the square root, that's np dot square root, of xp minus x number n squared, that's this part of the formula, plus d, close parenthesis, and that's it. That's y. So then we want to plot it. plt.plot x versus y. Oh, but that should probably not be x versus y because we call that xp. So it's xp versus y. And we hit shift enter. And there's our figure. Oh, we want to add some labels. X label, xp, y label, yp, y. Of course, it's not called x label. It's called plt.x label and plt.y label. There we go. That's exercise 1. Exercise 2. The file measurementlocations.dat contains the x and y values of 20 measurement locations, where both x and y fall between -100 and +100. In addition, consider the straight line y is equal to x from minus 100, minus 100 to plus 100, plus 100. Perform the following tasks. Plot a red line from x1, y1 to x2, y2. Load the measurement locations. Plot a blue dot for each measurement location that is above the red line and a green square for each measurement location that's below the red line. Compute the vertical distance between every measurement point in the line y is equal to x and plot a black cross for the measurement point that is closest to the line. And make sure the scales along the axis are equal. All right, there we go. First of all, we do plot from x is minus 100 to 100 and y is minus 100 to 100 with a red line, and it's called plt.plot. And there's our line. We wanted to do x is equal, plt.axis equal. So we get the line to look at a 45-degree line. The scales are equal along both sides. We load the measurement locations, and the file name is given here. So let's be lazy and copy that so we don't have any typos. We say the XY locations is equal to np.loadText, file name between quotes. And then I don't really know how many I have, so let's print np.shape of xy to the screen so we know what we got. Apparently the xy values I have 2 rows and 20 columns. So row 0 are the x's and row 1 are the y's. Which means we can probably say x comma y is equal to xy. Print x, print y, just to see what we got. Those are the values we have in there. Now the next question was plot a blue dot for each measurement location that is above the red line. All right, so we going to do that. plt.plot. And then we have all the values of x where y is larger than x. And we have all the values of y where y is larger than x. And we want to plot a blue dot. Let's see if that worked. That looks about right. Then we do the other ones. plt.plot. We want to plot a green square for each measurement location that's below the red line. So it's the same syntax, but now y is smaller than x, y smaller than x, and we want to have a green square. There they are. Last question. Compute the vertical distance between every measurement point and the line y is equal to x, and plot a black cross for the measurement point that is closest to the line. All right. All right, we can simply calculate the distance as distance is equal to y minus x, right? So it's the y value we have stored here minus the line we have, which is y is equal to x. And we wanted to find the smallest one, so the closest one is equal to, and we want to have the argument of that, np.argmin gives us the argument or the index of the point that's closest to that line, and all those distances can be positive or negative, so we need to take the absolute value of the distance, or you could take the square root of the distance squared. That's just for kicks. Print out what the closest point is, print closest, that's apparently number 11, and for that we had to plot a black cross. Plot x closest, y closest, and we had to do a black cross. Not black cross, because what's named plot is not defined. It's called plt.plot. And where's the black cross now? I don't see it. Oh, she does make it a black square, because you can see the black cross unless you make it really big. There's the black square. Don't like it very much yet either. Looks like a blue square. Oh, it looks like a blue square because black color is K. There we go, the black square right there. That's the end of exercise 2. Exercise 3. Consider the following simple game. You flip a fair coin. When you win, you receive €1. When you lose, you have to pay €1. When you play this game for a long enough time, you will not win or gain any money, provided you don't run out of money when you hit a long losing streak. The file coinflipgame.dat that contains the outcome of 1,000 games, where a value of +1 means you win the game and -1 means you lose the game. You start the game with €10. Plot your money versus the number of games allowing your money to go negative. Determine after which game you run out of money by using a loop, so not just by looking at the graph. Report the highest amount you ever had before you ran out of money, again by computing it and not by simply looking at the graph. Alright, well, let's first load the game. Game is equal to load text, np.load text. Coinflipgame.dat. That's the game. np.shape. See, we have 1,000 numbers in that game, so that looks about right. All right, then our money is equal to 10. And we want to start this game with 10. And we have 1,000 games, so we need an array of 1,001 length. So really what we should have said is money is equal to np.zeros of 1,001. And the very first one, money number 0, that's before we start the game, is 10. Then we do a loop for I in range 1,000. Money number I plus 1, right? The first time is after game 1, so there should be I plus 1 here. With game 0, or when you start number 0, it's 10, is equal to the one we had before, money I plus whatever the game is, number I. Right, so when I is equal to 0, it says here money number 1 is equal to money number 0 plus game number 0. And we do that for all of them. Once we're done with that, we say plt.plot money, and we'll see what the graph looks like. There's our graph. You see that there's 1,000 games, and with this series of coin flips, we never go above $20 or €20, but we eventually, after some 300 and some games, we'll go down to 0 and we'll run out of money. And our question was, determine after which game you run out of money by using a loop. There we go. For I in range, well, there's 1,000 of these. If money number I plus 1, right? So that's the game number, is equal to 0, then we say break. Right, so we keep doing this loop until we run out of money, and then we print game where we run out of money is number I plus 1. And it is game number 336. That is the game where we run out of money. Then the last question was, report the highest amount you ever had before you ran out of money. And it looks like it's 20, but let's try to find that. So we do np.max of, well, we can just actually do the entire range. We can just do money, because we see from this graph that we never go above that. But really we should say for money from 0 to number 336. And we print that to the screen. Print highest amount we ever had was $20 or €20. That was exercise 3. Exercise 4. Consider the sawtooth-shaped function shown below. Run the code cell below. So let's run this. Oh, it looks like that. It's called a sawtooth-shaped function. The sawtooth-shaped function shown above can be approximated with the following Fourier series with n terms. Y is approximately equal to the sum of 2 over n minus 1 to the power n plus 1 times the sine of n times pi times x. The more terms you use in the Fourier series, the better the approximation becomes. Write a Python function that takes as input arguments an array x and the number of terms n, and returns the Fourier series approximation of the sawtooth function using n terms. Plot the Fourier series approximation versus x for x varying from minus 2 to 2, for n is equal to 5, n is equal to 10, and n is equal to 50. And of course, you will see then that the approximation should get better and better, and it should start to approximate this blue sawtooth-shaped function. Finally, add a legend to the graph. All right, there we go. We first have to write a function, def. Let's gonna call it Fourier. And it takes as input arguments x and capital N, colon, enter. And it has to return some y values. So y is equal to, and we're gonna have to do again a summation. So at first should have 0 values, and it should be an array of the same length as x. Is equal to np dot zeros. Well, we could do zeros, so the length of x, or we could use the other cool function we've learned, zeros like x. So it's an array just like x's, but then filled with zeros. And then we say for n is in range from 1, that's the smallest value, and the last value is capital N, so we go to n plus 1, because remember, range stops before it reaches that. Y plus equals, right? So y is equal to y plus, and then we have to implement this formula right here. 2.0 divided by n times minus 1.0 to the power n plus 1 times the sine, which is called np.sine, of n times pi, which is np.pi, times x. And finally, the function returns y. And we want to calculate this function for 3 values of capital N, 5, 10, and 50, and x should go from minus 2 to 2. So x is np.linspace from minus 2 to 2 with 100 points. y1 is, we're going to call this function Fourier with these x values, and n is equal to 5, capital N. y2 is the Fourier series with these x values for capital N is equal to 10. And y3 is a Fourier series for these x values for capital N is equal to 50. And we plot it. plt.plot x versus y1. And I'm going to add a label to this instead of doing the legend like we've done in the past. N is equal to 5. If you do this label thing, you don't have to enter any text anymore in the legend. It will do it for you. It will use whatever you call the label. So this label will show up in the legend. So we plot y2 and we plot y3. Label is equal to n is equal to 50. We do plot. We have already done plot. And we say plt.legend and let Python figure out, or matplotlib figure out the best location it can find. And that should do it. Shift enter. There we go. This is our sawtooth function. The blue line is for only 5 terms, and you see it wiggles around what it should be, but it's reasonable. The green line, it uses 10 terms, is already a better approximation. The red line is 50 terms, and that's pretty darn close to this line here we showed you before. That's the line we try and approximate. That's the end of exercise 4, and that's all I got for you today. I hope to see you next time.